Hi, and welcome to the talk on indoor storage research. My name is Brandon Hopkins. I'm an assistant research professor at Washington State University. So today I'm going to be talking about some of the indoor wintering and indoor storage research that we've done here at WSU, starting with some of these components of nutrition and the use of CO2 to increase varroa mite mortality during winter storage. And then this artificial brood break and queen banking is really the use of indoor storage facilities at times other than the winter period. So this idea of indoor storage of bees is nothing new. In Canada, they've been doing it for more than 100 years. These are some pictures of beekeepers in Ottawa moving colonies into a cellar situation. And even in the US, it's not particularly new either. Here's an article in the American Bee Journal from 1902. It's really a beekeeper writing in a question to Dr. Doolittle here, asking about how he prevents losing a third of his colonies each year during the winter, with the advice being that he could move his bees indoors into cellars or use these chaff hives. But here in the US, it's really on to a much larger scale. For example, a building like this one here, specifically designed to hold colonies. I think it's designed to hold around 40,000 colonies. Uh, the entire building designed around that with the slats in the wall there, that plenum, to push air down between the stacks of colonies. Those lines on the concrete there are where the hives are stacked up with airflow between them. In a building, it can look something like this. But it's quite impressive, the scale that they do this at. Our interest in it really came from a beekeeper in Washington State that was having success doing this in comparison to storing his bees in California holding yards. The first sort of observational study we did was looking at a set of colonies that we had set up about 14 frames of bees each in October. These are here. CA room is a controlled atmosphere room that was really originally designed to hold tree fruit like apples. In the same facility, they had sort of a standard refrigerated room, highly ventilated, and a set of colonies that were just outside that building in Natchez, Washington. And it took some convincing, but we had him also send some of those colonies back down to California in the holding yard situation that he had done for many years. And so when these colonies were all shipped down to California in January, near the end of January, we assessed those colonies again, and this is the average frame strength. So really no difference between the colonies that are held in either of these two indoor rooms or the colonies that were held outside in Washington, which really had an average temperature of around 40 degrees, kind of similar to these indoor buildings. But the colonies that remained in California during that winter period was the main significant difference, and those colonies came through the winter only averaging about 6 frames per hive compared to almost 11 frames per hive in the colonies held indoors. Looking at a number of different factors. One of these is nutrition, and we have a paper that is in its second round of revision in press on the sort of physiological state of these bees when they go through indoor wintering. So we painted a massive number of bees in the late fall, and we installed those painted bees into a set of colonies on pallets, so that some of the colonies were sent to California, some of the colonies went to the refrigerated storage facility, some sat outside in Washington, and some went into this controlled atmosphere facility. So from that, we were able to collect, recapture these bees after the winter storage period. And so this is the head protein levels, the protein level being in the hypopharyngeal gland in the head of the bees that we recaptured. And there was significantly more protein in that hypopharyngeal gland in the bees that were stored indoors compared to the bees that were stored outdoors in California. We took the rest of the bee and we did a lipid extraction. So this is the fats that are in those bees. and there was significantly more fat in the bees that were held in colonies in the controlled atmosphere facility compared to the California holding yard. And so this kind of aligns with what we saw in those observational studies, or at least provides maybe some explanation for why there were more frames of bees per colony in those that were held indoors. One of the next things we did, because of our access, or that beekeeper's use of a controlled atmosphere facility, was probably more of a concern than anything else, was the CO2 levels rise quite a bit in those controlled atmosphere facilities because they're so well sealed and there's very little ventilation. And fortunately, we had some work to go off of based out of Rob Curry's lab, in which they used caged bees in low ventilation, high CO2 levels, showing increased varroa mite mortality. And so we did this on single deep 8-frame colonies in incubators held at 4 degrees Celsius. And we had a high level of CO2, basically 8% CO2, in a control which was closer to normal atmosphere levels. And so what we found over a course of 62 days was a varroa mite mortality about 75% in those colonies held at high CO2, and a varroa mite mortality in the control group of around 45%. So still building on this use of indoor storage for varroa control, there is this advantage of indoor wintering or storing indoors that allows some control over the brood, the amount of brood in a colony. You can sort of take advantage of this to control varroa mites. So most of the commercial products we have to control varroa mites really only work or are effective against these phoretic mites. So once the mites crawl in to the capped cells, they're fairly well protected from the mite control options that we have. Found this in one of two ways. They can either be like long-lasting strips, like the apivar strips, these slow-release compounds that last a brood cycle or more, or Hopguard, for example. Or you have sort of these flash treatments like oxalic acid that need to be reapplied every week or so over the course of a brood period. And this is all designed to get around the fact that the mites are well protected inside pupae. That have, 100 colonies or less, or a few hundred colonies, and it's pretty widely used in Europe, is this queen caging, and it's highly effective. It just improves the effectiveness of these products we already have available. So here's a study showing that queen caging in combination with Apiguard is highly effective, or increases the effectiveness of that miticide against varroa mites. So with queen caging, it's 97% effective. Without the queen caging, it's 70%. And also with oxalic acid showing very similar results. So what we did was kind of look at whether we could do this with the use of an indoor storage facility at times other than winter. So the first thing we did was look at the time period of August. So after bees are done with vegetable seed pollination, for example, and put the colonies indoors for 18 days, bring them out, treat them, a single application of something like oxalic acid, for example, to increase the effectiveness of the mite control, and it was highly effective. I think it needs to be said that it is important that a beekeeper looking at this option needs to have a really good access to a fall forage, so that those bees can kind of build back up, brood back up in preparation for winter. So based on that work, we also looked at the possibility of doing this in the early season or after almonds as a form of varroa control when they're full of brood and the beekeeper maybe has some time before they go to the next pollination set, or they're moving to a northern state where maybe the forage flow it really isn't on yet, and they feel as though they've picked up a lot of varroa mites during almond pollination. So that's what this figure here shows, is a large set of colonies that went indoors in April after almonds. And when they came out after 18 days, they received a single application of oxalic acid. And then this outdoor group is from the same set of colonies, but they stayed outdoors, and after 18 days received a single application. And it's kind of known, that a single application of something like oxalic acid is not going to be highly effective. And in this case, it just shows that a brood break in combination with oxalic acid using indoor storage can be a highly effective mite control. But by going indoors for 18 days that early in the spring, that they might lose out on honey production. We weighed these colonies at day 0 going in, 18 days, and at 55 days. And the colonies that went indoors showed no reduction in weight gain over that period of time. It could just be that the outdoor group didn't have a lot of forage available to put on weight during that time of the year in that location. Or it could even be that the higher level of varroa in this outdoor group was really holding them back just because of the parasitism of the mite. And this is, I guess a little out of order, but this is that fall treatment. And the big deal here really is these error bars. And so for one thing, the indoor group, because they are almost entirely broodless for that treatment, not only is the treatment effective, but it also is consistent. So these error bars really, as a way of looking at it, is the consistency of the treatment. So while there's brood, a single application is highly inconsistent, whereas when they're mostly broodless, you get a high level of consistency and something that you can depend on. So those are extra slides. Sorry about that. Okay, so then this was the concept here was looking at the brood area as a form of management and swarm control. So this just shows that you have an indoor group. The blue is before storage, so this is really from the same set of colonies. There's no difference in these blue bars. We just designated one set of colonies as indoor. They went indoors for different sets of time. I'll get to that. And there's an outdoor group that's just remained outdoors. So those colonies continued to grow or continued to increase the amount of brood that they were producing over this 18-day period, whereas the indoor group dropped dramatically in the amount of brood area that they had while they were indoors for 18 days. The beekeeper wanted to see the minimum amount of time, and so, like I said, so not only for varroa control, but also as a management strategy for an operation that has so many colonies that it's impossible to get around to them in time to prevent swarming. The idea was, could you take a portion of an operation out of the field and into a building in order to basically increase the effectiveness of the crew to get around and make splits before colonies swarm. So we had a set of colonies in for 12 days, 14 days, and 18 days. After only 12 days, 45% of those colonies within a month attempted to swarm. At 14 days, a third of those colonies tried to or drew out queen cells in an attempt to swarm. But after 18 days, none of those colonies drew out swarm cells in the time period we observed them. So this was an effective form of swarm control as well as a management tool. The project we have going on currently, and so this work was inspired by Andre Rousseau's lab in Canada when we saw this data holding queens over a winter period at 15 degrees Celsius. They had an 86% survival rate, which is amazing. It's very impressive, and we thought we could try something similar but in a summer period. And this is based on the fact that in one of the places where they produce a lot of high value, high quality queens in Northern California, it can be very hot. And if you've watched the news, it can also be prone to wildfires. And so there's weeks on end when the temperatures are above 100, and it can be difficult to bank queens when the conditions are like that. So what we did is compare banking queens outdoors in Northern California in this heat and in the wildfire smoke compared to banking queens indoors in a controlled temperature in a facility. So we used a little over 2,100 queens split between that outdoor group in California and an indoor group in Washington. And within each of those groups, we had different stocking rates for the banks. So we had a set of banks that had 50 queens each, a set of banks that had 100 queens each, and a set of banks with 200 queens each. And those were sampled for analysis at David Tarpey's lab at North Carolina State University for queen quality controls, but also installed into nukes in the field for brood quality assessment to look at the quality of those queens, in addition to queen mortality. And that data is being processed right now, and those just came out of their banking period and are being installed in nukes right now. So I'd like to thank the folks that graciously funded a lot of this work, Project Apis M in particular, the Washington Tree Fruit Research Commission, the Almond Board of California, Washington, Idaho, Oregon State Beekeepers Association for their funding. There's also a number of graduate students that have been participating in this work and have been wonderful. Anna Webb and Stephen Onyemi have been wonderful at working on these projects. Thank you.